Hello everyone, NNNI here, and after the surprise success of my trailer video, I thought I'd do one more, and this time, finally, I've decided to show you my capacitor charger and the fact that it actually works and can charge capacitors relatively quickly. So before we go into anything else and how this thing works, I'll show you how fast it can charge. This is my multimeter set up to measure the voltage across my capacitor bank, which is 2000 microfarads at 200 volts. This is my capacitor charger. This is the button with which you start charging, and this is the main power switch. Alright, so let's go. First, I turn this thing on. A green light comes on. My multimeter is going to read the voltage across the bank, and I start in 3, 2, 1. Done. Simple. 200 volts in no time. And the reason why this voltage drops so quickly is because of this 10K pot which is reading the voltage across the bank and feeding it into a comparator. So this is basically the working of my capacitor charger. The thing with this capacitor charger is, using this potentiometer you can control the charging time, and how that's done I'll tell you later. The red light stays on till the capacitor voltage reaches a safe level, and I have my oscilloscope set up and ready so that I can show you some waveforms. First we'll be measuring drain voltage. This is the 0 volt line over here, and it jumps up to 12 volts. I've set it to trigger at around 14.6 volts. The capacitor bank is almost discharged now, so we can charge it again. And this is what the waveform looks like. In 3, 2, 1. Oh, oops, I forgot to put it on single mode. Stupid me. Use this 1K resistor and this pair of pliers to discharge the cap safely. Okay, done. Okay, now I put it in single mode again, and I start charging once more. 3, 2, 1. Done. And this is the resultant waveform. And I know it doesn't look very good. There's still a lot of these high frequency oscillations which are undesirable. So I guess I have to fix my snubber network, which is this capacitor, this resistor, and this diode. Still some work to be done, but for now it doesn't look too bad. 2, 3, 4, 5, 6, 60 volts peak to peak, which is not very good. I don't think my transistors are going to like that. It's a MOSFET. And now we'll be measuring gate voltage. So I hook up the oscilloscope probe to gate. I make a few adjustments. Set the trigger level to something reasonable. Put it on single mode, and I start charging again. Done. And this is my gate waveform. Not too good, but it works. And I guess all this is because of the capacitive coupling between gate and drain. So if I fix my drain waveform, maybe this thing will get fixed. So that's pretty much it for now. I'll discharge this thing. Okay, ouch, that was not good. And let me charge it up again. 3, 2, 1. If you noticed, my current meter momentarily goes off scale. I don't know why, but it consumes around 8 to 9 amps pulse, which is okay for most portable applications using lithium polymer batteries. So this is basically my capacitor charger. And I also wanted to show you the circuit diagram. Ouch, sorry. So I have here my old diary in which I record all my stuff. So this is my old ZVS, etc. And right after the inter-school competition last August, I came up with this, a full bridge converter using TO92 NPN transistors, which is a terrible idea by the way, and an NNNI 84 or something like that for the PWM. that didn't work out very well. I didn't test it, so I abandoned it. It was too complicated. And sometime in October, I finally came up with something like this. So this is almost what I'm doing. Oops, so sorry for all the accidents today. I don't know why this is happening. So this is what I came up with. I'll walk you through it. The first section is my 555 oscillator. As you can see, I've hooked it up as a variable duty cycle and a variable frequency drive, which obviously I didn't do. So this thing right here is a 555 timer, and I've set it up as a variable duty cycle fixed frequency around 73 kilohertz. So this is how you can control the charge time. Higher duty cycle means higher current and lesser time to charge. And you can adjust this depending on the current ratings of your voltage source. It can draw as little as 500 milliamps and as much as around 10 amps. So I haven't been using this, but this is the heart of this whole flyback converter. And this is a 555 configured as a flip-flop. So if you press this switch, pin 2 is pulled to ground and the output goes high, which is indicated by this blue LED. If you noticed, when I pressed the charge button, it turned on. And then the op amp, which is set up as a comparator, I'm not using the same configuration, sends a reset pulse as soon as the voltage is exceeded to this transistor, which pulls pin 4 low and turns off this blue LED over here. So that's what the functionality of this is. Op amp as comparator, and this is a basic flyback converter. Obviously this is not the exact thing. So if we can go forward a few more months, maybe many months actually. This is what I plan to do with my railgun, by the way. Lots of math and code. This is more, no actually this is not more like it, but this is the comparator configuration I'm using right now. The inverting input is connected directly to 5 volts and the non-inverting input is connected to the capacitors through a 10K potentiometer. The red LED which indicates that the charging is done. And the most, I guess this is the most recent configuration of my 555 timer. Pin 3 output is directly connected to the capacitors. I'm not using the same values, but the diodes which I'm using right now are 1N4148s, 100K potentiometer, no resistor here, and my capacitor is 101, which is around 100 picofarads, I think. And that is the most, no, actually no, that's not the most up to date. This configuration of my flyback converter is most up to date with the snubber on it. I'm using a separate gate driver though. And yes, that's pretty much it. A closer look at my circuit, I'll walk you through it. So these thick wires are the input wires, as you can obviously see. Transformer, 2 smoothing filter caps, and this capacitor over here and this capacitor over here, the blue one and the orange one near this MOSFET, are for 0 voltage switching. I'll explain where I got that idea from. This is my 555 bistable op amp comparator, the transistor, the switch which is hooked up to these 2 pin headers. Oops, I charged it by accident. And this is a 5 volt regulator here, TO92. This is my oscillator board. This is a gate driver, 555 smoothing cap, all sorts of stuff. And I fit everything into something that's around the size of my thumb for comparison. It's very small. So this is pretty much it for this video. I'll link some of the waveform, I won't link, I'll attach some of the waveforms at the end of the video so you can have a better look at them. And for the ZVS thing, I got my inspiration from this research paper, which I link in the description. And this video is already turning out to be very long. So thank you for watching, and I hope to see you soon.